Hi, welcome to another topic in calculus, approximating areas under curves, and in short we call it Riemann sums. We're going to start with the velocity of an object is given by v equals 2t plus 1 meters per second, and the interval is from 0 to 4, n equals 2. We're going to use left Riemann sum to start with, and as we have the interval from A to B in general, ours is from 0 to 4, so A is 0 and B is 4. N equals 2, that means we're just starting simple way, which is two intervals. We're gonna divide the whole interval from 0 to 4 into two subintervals, which means we're going to go from 0 to 2 and from 2 to 4. That will make it a total of two subintervals. Here's a graph to help understand Riemann sum. The line right here represents 2t plus 1. Since this is t, I can call it x. Slope is 2 and the y-intercept is 1. It reaches up to 9 when t equals 4. 0 to 2 is my first interval. 2 to 4 is my second interval. Because I'm using left Riemann sum, I'm kind of like highlighting the 0 and 2. Let's see how. This is my first interval, and this is the base for the first bar right here. Since I'm focused on left, I'm gonna build up the bar and stop at the height that I get it from the image, the output of 0. 0 goes up to 1, so I'll stop at 1 and I'll close it. Second interval is going from 2 to 4, and my left part is 2. 4 is my right. I'm not going to use the 4. My left is 2. From 2, I reach out to the graph and I'll stop right there. So I'm building the bar based on my left. 2, f of 2 is 5, because 2 times 2 plus 1 is 5, and I'll stop right there. So instead of having all the area under the graph from 0 to 4, I'm building two bars using the left to determine the height of each bar. So the Riemann sum will say, left Riemann sum will add up with A1 plus A2 as A1 area for this right here, and A2 as the area for this right here. The left hand grid points are 0 and 2. Alright. The length of each subinterval, since n equals 2, formally we do it this way, b minus a divided by n. That's 4 minus 0, the whole thing right here, divided by 2 to find two subintervals, which is n equals 2, and I end up with 2. So I end up with two subintervals, gives me 2 as a length for each. That's the length. Alright. So what is the left Riemann sum? V of 0 times 2, V of 0 times 2, plus V of 2, V of 2 times 2. That's called base, and the height I get it from the left of the intervals. V of 0 is 1, as the graph shows. V of 2 is 5 right there, and the base is 2 and the base is 2. That's the 2 that repeats pretty much everywhere. Do the math, you get 12 meters. Why 12 meters? Because we're dealing with an application, and this is gonna be called the displacement. Area under the curve or the graph of velocity will give me displacement. The velocity is meter per second, and the time is seconds. When you multiply width times length or base times height, you're actually multiplying the base, which is time, with seconds, and the height, which is velocity, meters per second. So when you multiply them, velocity times time, paying attention to the units, meters per second times seconds, second cancels, and you end up with m, and that's displacement. So this is a great example to start with to understand left Riemann sum. And why do we care about areas under graphs or curves? Because areas as an x and y maybe doesn't make much sense, but now with this right here, it shows that the area under a graph of a velocity from 0 to 4 in this example gives me the displacement. So the object that was moving with a fixed speed of 2t plus 1 from 0 to 4 with a fixed slope, will give me a displacement of 12 meters from its start location. Okay, now let's take care of the right Riemann sum. If we have a left Riemann sum, we're gonna have a right Riemann sum. Kind of like makes sense what's going on. And before I move on, one thing I want to mention also, that as you could see right here, we're losing this part. We're not calculating that, and we're losing this part. So if the graph is increasing and we're using left Riemann sum, we are underestimating. So the actual displacement should not be 12, should be more than 12. Hopefully that is clear. Okay, right Riemann sum. Same problem, all right? Same graph, but now we're using the right. You see the 2? You see the 4? For this interval, 2 is my right. From 2 to 4, 4 is my right. So I'm going to build the heights based on my rights. The right-hand grid points are 2 and 4. Right Riemann sum will be a v of 2 for the first interval, not v of 0, times 2, of course, which is the base. This is the height, this is the base, height, base. V of 4 for the second interval, or the second bar, and the base is still 2. Do the math, I get 28. Now I got 28, and earlier, what did we get? We have 12. Well, because I'm not partitioning it enough, there is a huge difference, as you could see. But the Riemann sum starts with a great concept, as you could see. The whole calculus starts with a great concept when we start with. The limit concept is mainly the big deal for calculus, because without limits, applying it mathematically, it's kind of hard to solve problems and move on to advanced math. Let me show you what do I mean. So if we understand right Riemann sum, which is an overestimate in this case, because I'm gaining this part and this part that don't belong to my graph, they're not under my curve as an area that represents displacement. This is called an overestimate. That doesn't mean like the right Riemann sum is always overestimate. It depends on the graph, if it's increasing or decreasing and so on. You have to pay attention to the how does it look like and so on. Just make a note out of it. So if the left Riemann sum is underestimate and the right Riemann sum is overestimate, how can I make things more accurate or close to be accurate? Well, here's the deal. If I partition it to 2 intervals, I'm gaining too much or I'm losing too much. How about if I partition it to, instead of 2, make it 4 subintervals? How about 8? How about 8 make it 16? How about 16 make it 32? How about 32 make it 64? And so on and so on and so on. Well, by hand, you could do it, but it's time consuming. With math, once we get to the pattern that's happening, we could say we're gonna partition it n times such that n goes to infinity. Or we could say that we're gonna partition it to n times with delta x for each subinterval as a width, and delta x will vanish or will go to 0 as a limit. That means those bars, you're not going to see them that way. You're going to see them too tiny, too skinny. Pretty much it's almost like, you're using a pencil and you're graphing it, or you're shading this all the way. So that's the limit concept. Riemann sum is a great concept. You start with this idea and you take it further with the limit. Eventually, you're gonna cover everything down here and nothing above. Imagine if I partition this not to 2 subintervals, 1,000,000 subinterval. How does it look like as a graph to you? I think I'm gonna be like too close to the graph. I'm not gonna go that far. You get the concept, right? Okay. Now, since I have the slides and the graph, and this is a simple graph to understand, we do have left Riemann sum, we have right Riemann sum, we have midpoint Riemann sum, we have even after that trapezoid and other methods. But the whole idea starts with Riemann sum, left, right, and mid. Here's mid. Midpoint Riemann sum. Here is a graph with the midpoints or the focus points to build the height for each subinterval. From 1, I'm going to reach up to 3 and end up right there. From 3, which is the middle of the second interval, I'm going to reach up to its image, which is 7, and stop right there. So this will be 2 times 3, and this will be 2 still times 7. The midpoints are 1 and 3, and v of 1, 3, v of 3 is 7, same basis, 2 and 2, and now 20. 20 is more accurate, as you could see. Let's take it back a little bit. I went too fast. That's kind of like in the middle. You remember last time it was overestimate with 28. 28 is a little bit too high, and the graph shows it. Because we're understanding, or we're going over areas under the curve and the importance of area under the curve, how about if we do it exact? Well, sometimes you could do it by hand without this concept left and right. You could partition it to 2 parts. Because my triangle, if you see the triangle, is not sitting on the x-axis, it starts from 1. I'm gonna partition it to area 1 and area 2. Area 1 is base times height, which is a rectangle, 4 times 1. And area 2 is a right triangle, half times base times height, half times base times height, half times 4 times 8. From 1, level 1 to 9 is just 8 for now. And the answer is 16. 4 and 16, add up the areas, 20 is the actual. It looks like the mid point was also actual because it was balancing both. Take a look. What I gained right here that doesn't belong to me is equivalent to this, kind of like balances out. I lost this, but I gained this. I lost this, but I gained this. That doesn't work all the time, because if it's a curve, it's more accurate midpoint, but still, when it's a line, it looks like it gave me a good job. Here's the bonus. Since Riemann sum is giving me area, I want to move ahead and move on after we apply the limits with Riemann sum. We're going to take you to the integration. So let me give you more about the benefit of Riemann sum and what's going to come after Riemann sum. The velocity of an object is given by 2t plus 1, same interval, same number of partitions. Area under the curve of f of x on the interval from a to b. If f of x is positive, sitting above the x-axis on your interval all the way, then the area under the curve or the graph of the function will be called the integration from a to b of f of x dx, which means with respect to x as my main variable. The integration of x to the power n dx from a to b will be x to the power n plus 1 over n plus 1 from a to b. What do you mean by this? You take the x to the power n, you increase the exponent by 1, becomes n plus 1, and you divide by that n plus 1. So you make a denominator of the new exponent n plus 1. This is the opposite way of differentiating. When you have x to the power 7, you bring 7 up front and you make the 7 as an exponent reduced by 1, which is 6. This one increasing it. That gives an idea about the integration is also the inverse of differentiation. In case you have the same thing but without limits, indefinite integral, you will have to add a constant c. Don't want to go over too much detail because this is not within Riemann sum. It's a bonus for coming sections that the whole integration started with Riemann sum, and Riemann sum is a sum idea of subintervals multiplied by heights. Simplify the algebra, then you'll have a package that you need to keep doing it. And if you do it not 2 intervals, when n equals 2, you do it, let's say 4 intervals, you'll be more accurate. 8 intervals, 16, maybe 32, maybe 64. You get the idea. That means you're eventually approaching a concept that you want to partition the whole interval from a to b into subintervals that they are infinitely many. As n goes to infinity, you don't want to keep it 2, or you want to say as delta x approaches 0. That whole language changes to the formal integration symbol. This is the integration symbol. So back to the same problem. We said that the integration or area under the curve is called displacement. Applying the rules kind of quick, because that's not our topic one more time, but doesn't hurt to see it, because that's what's coming in the coming videos that I'm going to be recording. I have one after this, and tomorrow I'll have another 2 videos. 2, you keep it. T to the power 1 becomes t to the power 1 plus 1 over 1 plus 1. 1 becomes t. Simplify this. This is a 2, cancels with this 2. And the clean look is t to the second plus t. Let's double check backward. Find the derivative of this. T to the second gives you 2t, and t gives you 1. So the derivative of t to the second plus t is 2t plus 1. It's right there. Alright? So integration gives you 2 things. Gives you area under the curve. In our case, it's called displacement. And also gives you an inverse mode of differentiation. Integration takes you from first degree to second degree, where derivatives, differentiation takes you from second degree to first degree. So they are inverse of each other. Plug in 4 in this whole package. Subtract, plug in 0 in this whole thing. So that's what we are referring to. Do the math, you end up with 20 meters as an answer. Okay, so that's not just Riemann sum, that's Riemann sum in a different look, an advanced, sophisticated look instead of saying plus, 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 plus. Second example, This time I'm going to take x to the second. Doesn't have to be 2t plus 1 or simple straight line. A to b is from 0 to 2. N equals 4. So we're going to partition this 4 subintervals. So if you want to partition this from 0 to 2 into 4 subintervals, let's make them equal. It doesn't have to, but we want to make our life easier by going with equal bases or subintervals. What do you think the length of each subinterval is going to be? The way we do it is delta x equals b minus a over n. 2 minus 0, that's the whole thing, divided by 4 to find each, which is 0.5. I think that should do it, right? Look, this is the first interval from 0 to 0.5. My second interval is from 0.5 to 1. My third from 1 to 1.5. My fourth from 1.5 to 2. That's 4 intervals, identical width. 1, 2, 3, 4. Alright, now let's talk about the left Riemann sum. This is a graph just quickly to describe those numbers in a second degree from 0 to 4 to 2. 0 to 2. 2 will take you up to 4 and 0 will keep you at 0. The left Riemann sum is the following. First interval from 0 to 0.5, that's the width, times the height. You take it from the left. This is my left, f of 0. For the second interval from 0.5 to 1, my left is 0.5, so I'm gonna take the height from 0.5, f of 0.5. My third interval from 1 to 1.5, from 1 to 1.5, my left is 1, so I'm going to use f of 1 as my height, and the last interval, the fourth one, I'm going to take the height from 1.5, so I'm going to build and stop right there. 1.5 times 0.5. Notice the pattern that all of them, they have the same base. That's a bar, that's another bar, that's a third one and a fourth one, and they're all equal the same base. So I could reduce my calculations and save myself some time and take the 0.5 out as a common factor. You see, math is all about patterns and simplifying to make things easier for us. Now, notice also another thing. So if you want to skip this step and start from this step, you know this and you know why you have it outside. This is the base times the first height times the second height times the third height times the fourth height. 0.5, 1, 1.5, 0.5, 1, 1.5. I did not use 2 because 2 cannot be my left in any way. I'm using left. F of 0, f of 0.5, f of 1, f of 1.5, which is 2.25. Do the math and you end up with 1.75, and I believe this is underestimate, and it's not always underestimate for left Riemann sum. It's just because it's increasing and I'm using left. Look at the first one, f of 0 times 1.5. This is 0.5 as a width or base. If I take it from my left, I'm not reaching up anything. I'm keeping it flat with the x-axis, so I'm losing. And so on. Let's take care of the right Riemann sum and see the difference. Same problem, but this time we're going to use the right. Notice the following, and we are missing the 2. So in the right Riemann sum, on the first interval, when you look at your right to build the height, you're going to go like this. So you're not going to be looking at the 0. And this is what I mean. 0.5, 1, 1.5, and 2. Those are the heights, and that's the base. Start from my first interval. This is my right. I couldn't use 0 because it's not my right. 2 now was my right for my last interval. And if you do the math, you end up with 3.75. That's an overestimate, because the last interval will give you a bar that looks like this, because you're building it to the height of your right, which is up to 4, as you could see from here. Okay, let's take an example about sigma notation. And why do we need this? Because this right here is called a sum. And sometimes we look for patterns and we reduce our writing by using formulas instead of writing pieces of numbers. If there's a pattern between them, we could reduce our writing and make it look like this. It says express the following sums using sigma notation. Answers are not unique. Why is that? I'll start with the first one. 1 plus 2 plus 3 plus 4 plus 5. I could say it's a sum of k's, where k changes from 1 to 5. Yes, when k equals 1, I get 1, plus when k equals 2, I get 2, and so on. If you want to start from 0 back a little bit, you should end up at 4. You get the idea, right? 1, 2, 3, 4, 5, that's 5 numbers. 0, 1, 2, 3, 4, that's still 5 numbers. So if you step back a little bit here, you need to increase this one to balance it back. Let's test it. When k equals 0, 0 plus 1 is just 1. Works. The second is 1. I'm going to start with k equals 1. 1 plus 1 is 2. Let's go all the way to 4. 4 plus 1 is 5. Yes. So you could write it different ways. And as I mentioned, this sum notations will be the second step of Riemann sum as plus plus plus. We're going to write formulas. Then we're going to take it to the integration as a symbol way of writing sigma, applying the limit with it, taking n partitions, as many as we can, up to infinity, or making delta x goes to 0. And that's what we call it, the limit concept. Here's another example. 4, 5, 6, 7, 8, 9. It looks like there's a pattern from here to here. It's the same numbers, but I'm shifting them 3 units up. 1 became 4, 2 became 5, and so on. That's one way to say it. So instead of starting with k, I'm going to go with k plus 3. 1 plus 3 is 4. Look at the last one, up to 6. 6 plus 3 is 9. I think that should do it. So let's take another one. It's not always 1, 2, 3, 4. It could be with squares. Functions could be like x to the second. And I think it's clear why I'm writing k to the second, 1 to the second, 2 to the second, 3 to the second, all the way to 4 to the second. The last one could be fractions. 1 plus half plus 1/3 plus 1/4. That doesn't look like a fraction, but I could think about it as 1 over 1. So 1 over k. K changes from 1 to 4. And I think that should do it. Okay, that should do it for this video. And my second video is coming right after this. I'm recording 2 videos tonight. And the plan is another 2 videos tomorrow. Thank you for watching, and I'll see you next time. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.